Okay, all right. So let us start today's session. This is session number 18, and today we are going to see the left part of Gauss-Seidel load flow method, and then we will start today Newton-Raphson power flow method. So basically, we have seen that about what is the need of the iteration method like Gauss and Newton method. These are whatever we have equation that these equations are nonlinear equations, and to solve this equation we require this these iteration methods, and we cannot find the voltages and the current injections using the bus admittance matrix, because whatever the known quantities that are not the bus voltages or the current injections in the power system, we have the known quantities are either the power injected by generator or the power demand by the load. So for that we have to use the power balance equations, and these power balance equations also does not have closed form solution, so we go for the iterative methods like Gauss or Newton method. So we have seen this how we can derive this power balance equation. So in a multiple bus system you can derive this power balance equation using this simple expression xi is equal to vi I conjugate, and this here vi, if you want to calculate the voltage at the different buses, then you have to use this expression voltage at bus I. Now after finding this voltage at different buses, you you want to calculate the power active and reactive power injection at different buses. So you can apply below these equations. These below equations are also called as power flow equations. Pi and Qi. These equations are also known as power flow equations and very important for the in the load flow analysis. And with this help of equation, you can find the power injection at different buses. And after finding the power injections, you can find the losses in the system also. So this is quick recap about what we have studied in the previous session. Now coming to today's session, so let us have a quick example that I have also discussed in the previous session, but just we have to recap this. So this is a two bus power flow example. We are going to solve this question with the help of Gauss iteration method. Here we are given with a 100 megawatt 50 MVAr load is connected to a generator through a line with Z is equal to 0.0.02 plus J 0.0.06 per unit, and the line charging of 5 MVAr on each end is given. Also there is 25 MVAr capacitor at bus 2. If the generator voltage is 1.0 per unit, what is voltage V2? So we have to find this voltage at this bus 2, therefore using the Gauss iteration method, but before that we also need to find the bus admittance matrix. So let us first draw the equivalent circuit diagram of this given two bus system. So Z line is given as 0.02 plus J 0.06 per unit, and this is bus number 1 and this is bus number 2, and here we are having the load, and that load value is S load In the per unit it is given as 1.0 plus J 0.5 per unit. So all of you try this question. You have to apply this Gauss iteration method, and I have shown this expression of how you can find the voltage difference buses using the first equation. So you have to apply this first equation. For that you need to require this bus admittance matrix, different elements of by bus, so that you can put these elements and get the voltage at bus 2. So again here this capacitor is connected at bus 2, whose value is J 0.25. Anyone having doubt like here how this admittance of capacitor is coming as J 0.5? And you can represent line charging by this. We have taken the pi model. So line charging given of 5 MVR. So what will be the value of admittance of this capacitor? Anyone can tell? Admittance of this line charging element. Anil Biraya.
Sir, reciprocal of 1 by Z.
So it is coming as J 0.05. So how it is coming? Since 5 MVR is given, so you can directly 100 MVA the base MVA is 100 MVA. So per unit MVA, what will be the value? 5 divided by 100, so it is 0.05, right? So you can write Q per unit is equal to V square per unit into Y per unit, and if Q per unit is 0.05, Y per unit is given as 1.0 per unit. So from there you can find Y per unit. So you can calculate this way also. And Y admittance of capacitor is calculated in this way only. Now we are having all the elements of the line. So now we can find the bus admittance matrix. So here I have written down that we have to find the complex load voltage, that is V2, and we have to, for determining V2 we need to know the Y bus. So first I have calculated this line admittance y is equal to 1 divided by z, so it will be 1 divided by 0.02 plus j 0.06, that is 5 minus j 15. Now for y11 you have to just add all the elements that is connected at bus 1. So first is 5 minus j 15, that is line admittance, plus line charging admittance is j 0.05. So it is coming as 5 minus j 14.95. y12 and y21 will be equal symmetrical matrix. So this will be minus of y, and it is minus
Minus, so
5
yes,
plus
sir.
j 15. and this by 2 will be one extra element is there, that is capacitor. One capacitor is connected to the bus, so we have to take into account that value also. 5 minus j15 plus j 0.5 plus j 0.25, j 0.25. So what amount it is coming? 5 minus j 14.70. So we will get this bus admittance matrix. So this is very important. If you are solving any power flow problem, then you first need to know the bus admittance matrix. In university also, if you don't know, if you are not knowing the steps how to calculate the university exam, suppose a problem came but you don't know how to solve the power flow power flow problem. So first you just solve this bus admittance matrix, at least you will get some marks if there is a step marking. So but bus admittance matrix, to find the bus admittance matrix, it is very easy. So you can start with the easier step. Now we will apply this power balance equation, or how to find this voltage at buses. So here the general expression is Vi is equal to this one. Now you have to find the voltage at bus 2. So you put I is equal to 2. You will get this one, V2 is equal to 1 divided by 2 and so on. And here you have to eliminate this summation expression, since it is a two bus system and this k should not be equal to I. So only one expression will be left here. So it will by 2 1 V1. You will get this final expression where you have to put all the values. After putting all these values, like y22 will be 5 minus j 14.70, p2 will be minus 1 plus q2 will be j 0. How why have we have taken p2 is equal to minus 1? Anyone can tell? Anil Biraya. Q2 we have taken as minus 0.5. We have taken p2 as minus 1 per unit and q2 as minus 0.
Supplying the power, supplying the reactive power.
Yes.
Minus indicates supplying reactive power.
Yeah, yeah, but yes, you are little bit correct. So we are given this load power that is demanding power. So these power are not being injected at the bus. So in the general expression, if you see these expressions, these values are for the injected power injection at bus. Power injection at bus I. So here, whatever the value we are given, S load is equal to 1 plus J 0.5. These are not injected power. So injected power means you have to take the reverse. You have to add this minus sign. Therefore, we have taken this minus sign before before the value we are given. So you put these values, you will get and y2 we have been given with minus 5 plus j15. V1 is the voltage that is given in the question. So after putting all these value, you will get this general expression. Now we are going to apply this Gauss iteration. So we have to assume some value. So generally what we assume some this flat start, one at the angle of 0 degree. So in the power flow problem, we assume the flat start. So wherever you finding the voltage, just assume this voltage at bus as one at the angle of 0 degree. So you put this V2 star first, one at the angle of 0 degree. Here you put one at the angle of 0 degree, then you will get this expression, this one. If you put V2 0 is equal to 1 at the angle of 0 degree, you will get this expression. So this will be V2 1. And again, you, you got V2 1, then put this value again here, this V2 star. So this is second iteration. So V2 1, after putting, you will get this one as V2 2. And again, you at the third iteration, put V2 3 in the given expression, you will get V2 3. And again, in the fourth iteration, you will get V2 4, sorry, V2 3, you will get V2 4. So in the first iteration, we got the voltage at bus 2 at 0.967 minus this one, minus 0.0568. In the second iteration, you got this value 0.9624 and so on. In the third iteration, you will get 0.9622 minus j 0.0556. In the fourth iteration, you, in the third and fourth iteration, you got the similar value. If you take like more values be after the decimal, you may get different values, but I have taken four values after decimal, so it is moreover coming exact same. So we have to stop. If you want to, like, there is some tolerance, like you have to take the some epsilon value, that whatever the voltage getting at different iteration, just subtract the previous one from the newer. If you are getting that tolerance band, then you have to stop at that point. So here we are getting approximate similar, so we can stop here, and we can tell that this is the final voltage at bus V2, voltage at bus 2. So in the phasor form, you will get 0.9638 at the angle of minus 3.3 degree per unit, right? So any doubt how we have find the voltage at bus 2?
Yes, sir.
Yes, tell.
Sir, how did you think that ki first we put 0, 1, 2, 3 is similar? Oh,
This V value,
yes, sir.
this is the iteration, this is the iteration count. This is not V value, don't confuse. You are not putting V value anywhere in the calculation. This is the iteration count. Means this is like we are calculating, we are putting in mind this V2 0, we are putting as 1 at the angle of 0 degree, and V2 1 we are putting 0.967 here, this V2 star. This is the iteration count. We are not putting this value anywhere in the expression 0, 1, 2, 3, 4. This is the iteration count only, right?
Uh, sir, how you get one, 1 per unit and then 0.9621?
You just you are not getting this value. So
Yes, sir. I'm not getting.
here you will get V21 as 1 divided by 5 minus j 14.07. So we have taken 1, then this side is okay. So minus 1 plus 0.5 I and plus 5 minus 15 I. So top will be 4 4 minus J 14.5. So just divide this by 5 minus 14.7i. Sorry, 4 minus 14.5i divide by 5 minus 14.7i. 0.9671 minus 0.056. It is coming. So calculate carefully. I think you are not putting bracket after that. If you are using calculator, scientific calculator, then put bracket in the expression. Otherwise, it will, if you put 4 minus j 14.5 divided by 5 minus j 14 directly, then it will come different value. So I am telling you what it is coming. 0.967066 minus j 0.056856825. Anil, it is coming or not? Hello? Hello?
Yes, sir. Yes, sir.
Are you getting this? It is coming this value. V21 0.9671 minus 0.0568.
Yes, sir. Sir, we assume V2 equal to 1 and we put a V2 conjugate here and we get V1. V2 V2 1 and फिर we again we put V2 1 then we get V2 2.
Yeah, again, after getting this value V21, in the place of V2 star, you put this V21. Then you will get V22. That is second iteration, right?
Okay, sir.
Just we will just see how this, we will see more problems regarding this. In Newton Raphson also, we will see some this type of how we apply this iteration count or iteration method. Now, after knowing this, this is the actually this is the answer only in the problem it is asking. So this is the answer. But we can, after knowing the voltages, we can find the other quantities also, such as generator powers and the line flows. Generator powers you can find by SI VI conjugate. From there, you will get this generator power. These are all in per unit quantities. And if you, since base MVA is given as 100 MVA, so you can find the actual value. Now here one question I put that,
Sir,
yes.
sir, in last question we put V2 equal to 1. Sir, any question we always guess V2 equal to 1, sir.
Yeah, in the GATE exam, they will provide what you have to guess. But if it is not
Okay, sir.
given, then you have to assume this as 1 at the angle 0 degree. This is the conventional one. Means conventional, this is the like flat start. This is always be used.
Okay, sir. Okay.
So we don't assume 0.5 or 0.2, 0.3 like that. Because whatever the voltage at buses, it is moreover close to this value. So
But
that's why we take this.
sir, but we assume 0.5, then we also get more and more iteration. After that, we getting answer, sir.
Yeah, that is also great. Yeah, very good.
Okay,
That is
sir.
the thing. That is also you're correct. If you get
Okay,
zero
sir.
point 0.5, then you have to do the more iterations. That is also the thing.
And after iteration, lot of iteration, we get close to answer.
Yeah, correct. But for the ease of convenience, you
For convenience,
uh,
sir, we assume 1.
yeah. So it makes our life easy. So now,
Yes, sir.
so this is here I have put one problem. how much amount of reactive power the capacitor is supplying at bus 2. Because we are knowing this voltage at bus 2, you can directly find this voltage. You can find the amount of reactive power it is supplying. So Q Q per unit is V per unit a square. Sorry, V2 per unit a square into capacitor admittance per unit. So that is 0.9638 square into 0.25. So that is coming as 0.2322 per unit. So the actual amount of reactive power that capacitor is supplying is, you have to multiply with the base MVA 0.2322 into 100. So you will get 23.22 MVA. Now, so here the importance of slack bus comes into picture. Like we have seen in the previous example that there we have, it is specified that amount of active reactive power at bus 2 and the voltage magnitude and with its angle is given at bus 1, and we have solved for the power being injected by at the bus 1 and the voltage magnitude bus 2. So we cannot arbitrarily specify S at all buses because the total generation must be equal to total load plus total losses. So that is the thing. So we also need an angle difference bus. So we have to take the some reference in the power system. From there we can find the other voltage magnitude of, uh, by taking the angle difference of that bus we can find the voltage at the other buses. And also to solve these problems we define one bus as the slack bus. So this bus has a fixed voltage magnitude and angle and varying real and reactive power injections. So with this problem we have, whatever we have solved, we can know that what are the importance of slack bus exist in the power system. Because this slack bus provides this fixed voltage magnitude and angle, and also this is having varying real and reactive power injection. So that's why we can say that our total generation must equal total load plus total losses. If all the system have power generation and power demand is mentioned in the system, then how you can justify this that total generation believe must equal total load plus total losses. So that's this like was takes care, and it is having varying real and reactive power injection. And this both voltage magnitude and the angle both are specified. We have seen the Gauss method for the two bus system. Now suppose we are having many buses in the system, so then how we will apply this Gauss method? So with multiple bus system, this is the voltage expression is similar to the previous one, whatever we have seen this expression. And now put this SI conjugate equal to PI minus JI conjugate, you will get the below expression.
Sir, how we get these equations, sir? Vi equal to Vi power 1, V plus 1 equal to 1 by Y1, and this equation, sir.
This I have uh, uh, this I have discussed in previous session, but previous session was postponed to the on best day, like last on 20th December.
Yes, sir.
So
Yes, in last class, sir, you not taken, sir.
yeah, so don't worry, you can refer the previous video. So from there you can. This is very easy. You have to apply this thing for multiple bus system. You have to apply this power injection and current injection, and just apply the KCL. You will get this expression. So
Okay, sir.
then,
Okay,
but just remember one of this expression only. So finding the voltage at the buses.
Yes, sir.
Without knowing
Sir,
this expression, you cannot solve the power flow problem.
sir, you recorded this lecture, sir.
Yeah, I uploaded on YouTube also, and the Gate portal also I uploaded there.
Okay, sir.
So SI is equal to PI plus JI conjugate. So put SI conjugate as PI minus JI conjugate in expression. You will get the this below expression. Now here we can see that whatever this expression having the voltage values all are depending on the previous count. Means whatever the voltages we got in the previous iteration, that voltage it is coming here inside this function, and this outside it is having high one order higher VIB plus 1, and inside this function it is all having the voltage that we are getting in the earlier iteration. So this question is comes here that if you found this newer voltage quantity, then why you cannot apply the newer value? So here I have noted down that we have determined VIB plus 1, so we have a better estimate of its voltage. So it makes sense to use this new value. This approach is known as the Gauss-Seidel iteration. If you are not using the previous expression, previous voltage value in the that coming from the previous iteration, then that method is called as only Gauss iteration. And this Seidel has contribution only that whatever the we are getting values in the previous count in the previous iteration, we have to use the updated voltage quantity in the upcoming iteration. So that both of them make this Gauss-Seidel iteration. So we will see the example, and then after it will be clear. So in the Gauss-Seidel method, the new voltage quantity at V plus 1, that is VIV plus 1, immediately replaces VIV, and it is in the solution of subsequent equations. So that is difference between Gauss and Gauss-Seidel method. So now this Gauss-Seidel expression, how it becomes? So this is the general expression for Gauss-Seidel iteration. So
Sir, expression for Gauss iteration is different, and Gauss Seidel equation is different, sir.
yeah, it is different, but one slightly different. Like this is
Okay, sir.
Gauss-Seidel expression, general form, but you they no need to confuse like with a long expression. Just remember the Gauss iteration expression, this expression. Don't remember this Gauss-Seidel, the big expression. It is slightly bit looking more complex, and it is hard to remember. So whatever we have taken, if we are so we will see this with example. Now here this comes. So like there are n buses in the system. Suppose we are having n buses in the system. N bus in the system. And first bus is considered slack bus. So we are finding the voltage at 2, 3, 4 n. So for finding the voltage at V2, you will apply this Gauss iteration method, right? So that all values having whatever the values we have considered, that we have to take in this expression, right? So all values are previous values. Now you got updated value of V2. So if you are finding this V3, then you don't apply here V2V. Here you don't apply V2V. Here you are putting this V2V plus 1. That this expression you are putting here in this Gauss iteration expression. So that will be more uh, that will converge more faster than the Gauss method. So that is the thing. Did you get my point? Now again, if you are finding V4 V plus 1, then you put all these updated values. You are doing the first iteration only, but we are putting the all the updated values in the next buses whatever we are finding the voltage at the different buses. And similarly, you are finding V and V plus 1 like this way. You're you're knowing this V2 V plus 1, V3 V plus 1, V4 V plus 1, and so on.
But sir, for first bus we have to take a Gauss iteration, and then for second bus we can use a Gauss-Seidel iteration, sir.
For first bus is like bus na. First bus like, and I have one question so that it will be more clear. Now suppose you have to find V and V plus 1, this one. You are finding with the help of Gauss iteration method. Then what would be the expression? Anyone can tell? If you are finding this by Gauss iteration method, then what will be the expression of V and V plus 1? I think I should take one example so that it will be more clear. I have not taken example because I have not seen problem based on the Gauss-Seidel that is coming in the GATE exam. Moreover, many problems have come from the Newton-Raphson method, but no question have come from the Gauss-Seidel method that is little bit complex, little bit calculative. So Hn, Vn, V2, V. But for ESC point of view, it is very important. They will touch this point because without knowledge of power flow, you cannot become a good electrical engineer. Here I have written V and V plus 1. Here I have not used the updated value of voltage in this. So this will be the Gauss method only. Did you get some point or not? Little bit, I think it will be clear.
Yes, sir, clear, sir. We put V1 and then we put V2V and with V3 V, and we get from V1 we get V2, and from V2 we get V3.
Yeah, but in the
Yeah.
Gauss-Seidel, I have example solved in my notes, but I have not put here because that will make more uh, slides in the. So I have just means if you read any book, you can understand what I want to say. Just go after looking into it, go through in a textbook, it will be more clear. Means in Gauss-Seidels, if you are applying the first iteration only, then whatever the voltages, voltage you are getting a different buses, then you apply that in the next bus, you apply that value only. But in the Gauss method, you have to update the previous iteration values, not this whatever your voltage you're getting this iteration at different buses. So as this Gauss-Seidel works, means like how it works, it is better than the Gauss and it is actually easier to implement and it is used instead of Gauss. So you are using the updated voltages. That's why that's why it converges so faster than the Gauss method. So we usually use this method only. Now three types of power flow buses. We all know that load bus, like bus, generator bus, and this B parameters we calculate using this load flow, that PQ voltage magnitude and the voltage angle. And there are three main types of power flow buses. Load bus at which P and Q are fixed iteration solved for voltage magnitude and the angle. And slack bus at which voltage magnitude and angle are fixed iteration solved for P and Q injections. And the generator bus at which power and active power and the voltmeter are fixed and iteration solved for voltage angle and Q injections. So whatever the known quantities, we don't play with that quantity. Whatever we have unknown quantity, we have to find the unknown quantities for the respective buses. Now solution, we know that whatever the unknown quantity are different types of buses. For swing bus, once the load flow has converged, we use the equations for Pk and Qk to compute the real and reactive power. I have shown in the first slide only how you can compute the active and reactive power. That is also known as the load flow equations. So after knowing the voltages at different buses, you can apply this load flow equations. From there, you can find the active and reactive power for the swing bus. And for the load bus, you directly apply this voltage expression, power balance expressions. From there, you can find the voltage magnitude at the buses and the with angle also. For swing bus, it is already voltage magnitude and the angle is given. Both are given. So you don't need to apply these expressions for swing bus. You have to find this PK and QK, means like for whatever swing K quantity there, whatever the bus you have considered as swing bus, you have to find this active and reactive power for the that swing bus. And for voltage control bus, you have to calculate Qk and subsequently Qgk. If this calculated value of reactive power does not exceed its limits, then can be calculated, else this bus is treated as PQ bus. If the reactive power violation happens at the voltage control bus, then that bus is converted to PQ bus. That is very important. So generator reactive power limits. So the reactive power output of generators varies to maintain the terminal voltage on a real generator. This is done by the exciter. So in the real scene, the reactive power output of generators varies to maintain its terminal voltage, and this is done by the exciter. And to maintain higher voltage, it requires more reactive powers. And for generators have higher active limits which are dependent upon the generator's megawatt output. These limits must be considered during the power flow solution. Now this during power flow, once a solution is obtained, check to make generator active power output is within its limit or not. If the reactive power is outside of the limits, fix Q at the maximum or minimum value and resolve treating this generator bus as the PQ bus. So this is the important point. If the reactive power limit violation happens at the PV bus, then you have to treat that PV bus as the PQ bus. Violation of reactive power limit at PV bus, then PV bus is treated as PQ bus, right? This is also known as type switching, and this also need to check if a PQ generator can again regulate. And the rule of thumb is, as I said earlier, to raise the system voltage, you have to supply the more watts, and that is done by this help of exciter. Now if we see the Gauss-Seidel advantages and disadvantages. So it has advantages like each iteration is relatively faster, computational order is proportional to number of branches and number of buses in the system, relatively easy to program. Uh, so we need not that much robust computer, not much hard processing, means complex processing computer. Disadvantage is that it tends to converge relatively slowly, although this can be improved with acceleration. It has tendency to miss solution, particularly on large system. It tends to diverge on cases with negative branch reactance common with compressed lines. It is also sensitive to choice of slack bus. It needs to program using the complex number. So these are the advantages having this each iteration is relatively faster and it is relatively easy to program. Now two questions I have seen on the Gauss-Seidel flow method in the GATE exam, that is also a little bit older. Now all of you please try this problem. So the first problem is that in load flow analysis, a voltage control bus is treated as a load bus in subsequent iteration for a reactive power limit is violated. It is true or false? Anyone can answer this? Biraya or Anil?
True, sir.
Yes, correct. It is true. It is asked in 1995. Very older problem. It is of 1 mark. Voltage controlled bus means it is PV bus, and load bus means it is PQ bus. So when P bus is treated as PQ bus, when this rectifier violation happens. And the second portion is that the Gauss-Seidel load flow method has flowing disadvantage. Tick the incorrect statement. First option is that unreliable convergence. Second option is slow convergence. Third option is choice of slack bus effect convergence. Fourth option is good initial guess for voltage is essential for convergence. So yes,
Slow convergence.
no, that is incorrect. So
So choice of select bus affected convergence.
no, it is asking about incorrect statement. Read the question carefully. So this is also disadvantage, unreliable convergence.
Unreliable,
So this is also slow convergence. It is also there. Choi-
unreliable convergence.
Choice of select bus is also affects convergence. It is also true. These are all disadvantage of Gauss-Seidel. These are disadvantages of Gauss-Seidel method, Gauss-Seidel load flow method. And a good initial guess for voltage is essential for convergence. So this is not disadvantage. So this is you can treat as incorrect statement. It is asked in 2006. It is of 2 marks. Generally, verbal type question it did not ask of 2 marks, but here it is asked of 2 marks. Now this go all over all about the Gauss-Seidel load flow method. I have mentioned all the theoretical aspects of Gauss-Seidel load flow method. If you want to go more, then you refer in any standard book. After solving one or two problem about Gauss-Seidel, it is very means like it is not that much tough. You have to apply one or two equations only, and you have to do the iteration. But if you see any standard textbooks, it will looks like that what they are doing means like for first timer, it looks like it is very difficult. But if you just solve one problem of Gauss-Seidel load flow method like 3 bus system, 5 bus system, then it is very means like a cup of tea for you. Now for Newton-Raphson algorithm, so this is the second major power flow solution method, that is Newton-Raphson algorithm, and the key idea behind Newton-Raphson is to use sequential linearization. And in the Gauss-Seidel, we are using the quadratic linearization. And the general form of problem is that we have to find an absolute solution such that fx cap is equal to 0. So this is the steps for the Newton-Raphson method. Many of you have studied in the mathematics also, engineering mathematics also. So for each guess, we have to for each guess of x cap, that is the solution, absolute solution. We can xv the previous guess, define delta xv, x cap minus xv, and represent fx by Taylor series about fx. So write the function by expanding with the Taylor expansion, then you will get this expression. Now you take approximate function by neglecting all higher terms. All terms expect the first two. So we are neglecting this second order derivatives, and beyond that, so we will get the first expression and this single differentiation expression. Use this linear expression to solve for delta xv. So here you just sorry. So in the left hand side fx cap, and then it will be x v. Delta fxb. So on substituting fx is equal to 0, you will get you will get minus of fxv delta xv. So we will get this final expression of final this expression, that is fourth step. Now just solve for the new approximate of x cap, that is the absolute solution. And so these are the steps for the Newton-Raphson method. Now we will take one example of based on the Newton-Raphson method. So let us take the one example, that is x square minus 2 is equal to 0. So this equation we must iteratively solve with the help of the expression that is mentioned in step 4, delta xp. So here we have to first find the derivative of fx. So dfx y dx is equal to 2x. So you put 2xv and function of fx is xv minus xv square minus 2. Just put this in updated value of x. So xv plus 1, you will get this one. Now we will apply this initial guess and we will solve it iteratively. So on putting v is, on taking in the first, we have take the initial guess as 1. So x0 is equal to 1. So we will get what value we will get. So here we taking initial guess as 1. So x1 will be, x0 is given as, so take it as x0 first. X0 minus 1 divided by 2x0 x0 square minus 2. So whatever the value we have considered as initial guess, so x0 is 1 minus 1 divided by 2, x0 is 1, so 1 minus 2. So how much is it is coming? 1 minus 1 divided by 2, it is minus 1. So 1 plus 1 divided by 2, so it is coming as 1.5. So it is coming as 1.5. So x1 that is coming as 1.5. So I have mentioned at different points. So fxv is minus 1 and delta fxv is 0.5. So here in this way you can also calculate like xv plus 1, xv plus, sorry, delta xv. So xv plus 1 is 1.5, xv is 1 and delta xv is 0.5. In similar way, you can calculate for the next iteration. So this is the first iteration, and this is the second iteration, this is the third iteration. So you can find you will get the solution as 1.414, that is root 2. So if you're going beyond this value, then you are getting approximate similar value that is coming in the upcoming iteration. So you can consider this as solution if you are taking the if you are taking the value that is common after decimal as 3 point, then you take it as the solution. And the general points about Newton absorption is that when you are close to solution, then error decreases quite quickly. So this method has quite quadratic convergence. FXV is known as the mismatch, which we'd like to drive to zero. And stopping criteria is that you have to consider the epsilon value. That is, if it is beyond that epsilon value, then it is we have to stop that point. And one question here is that results are dependent upon the initial guess. What we if we have a guess x is equal to x0 is equal to 0 and x0 is equal to -1. We will discuss in the next class. Just think about this point. And the solution region of attraction is the set of initial guesses that converge to the particle solution, and the region of attraction is often hard to determine. So this is all about today's class, and we will discuss more about the for multiple variation. We will discuss more about this Newton-Raphson method for multiple variables, and we will also see the application of Newton-Raphson in the load flow expression. So we will complete I think first part in the next class about Newton-Raphson. It will take time because it has very complex expression, uh, so it will take time to cover this Newton-Raphson load flow method. Thank you, Anil.
Thank you, sir. Sir, but I think Newton options will complete in next class, sir.
Yeah, I will try to complete. I will try to complete. I will more means if I will not try, at least I will try to cover the all the theory part, and then in the and then after that class, I will try to cover the problems because many problems have been asked from the Newton-Raphson load flow. Okay, Anil.
Okay, sir. Okay, sir. Thank you, sir.
Thanks.